Today we're going to start chapter 4 with the chapter on elementary number theory and methods of proof. Start with the first section, direct proof and counterexample 1, the introduction to it. So, both discovery and proof are integral parts of problem solving. When you think you have discovered a certain statement is true, figure out why it is true. If you succeed, you know your discovery is genuine. If you fail, you may learn from it and discover why such statements is false. For complex problems, the interplay of discovery and proof is not reserved to the end of the problem-solving process, but rather is an important part of each step. So, assumptions about this that are made for this chapter. Assume a familiarity with laws about basic algebra. I'm pretty sure everybody here is at least Cal 1 level or above. So algebra shouldn't be a problem. 3 properties of equality, including the transitive property. Principle of substitution. If A equals B, then you can substitute B wherever we have A. And finally, there's the assumption that there is no integer between 0 and 1, and that the set of all integers is closed under addition, subtraction, and multiplication. This means that sums, differences, and products of integers are also integers. So even, odd, and prime and composite numbers. Integers, sorry. An integer is even if and only if that number is twice some integer. An integer is odd if and only if the number is twice some integer plus 1. Symbolically, n equals 2k for even, and n equals 2k plus 1 for odd, for some integer k. Use the definitions of odd and even to justify your answers to the following statements. Is 0 even? Yeah, because 2 times 0 is 0. 2 and 0 are both integers. So, is 301 minus 301 odd? Because for k equals minus 151, 301 equals 2k plus 1. And minus 151 is an integer. If a and b are integers, is 6a squared times b even? Yeah, because you factor out a 2 and it leaves you with 3a squared b, and 3a squared b is an integer because of multiplication and that sort of thing, because multiplication is closed on integers, so it's 2k, so it's an even number. If a and b are integers, is 10a plus 6 or 8b plus 1 odd? Yeah, because you factor out the 2 from the first 2 elements, and you get 5a plus 4b, which is a integer, times 2 plus 1. So it is 2k plus 1. And is every integer either even or odd? That one's a little bit more involved. But here's the first four. Yes, every integer is either even or odd. However, the reason for this fact is not immediately apparent. It can be deduced using the method of proof by contradiction. It is also a consequence of the quotient remainder problem. So, or theorem. An integer is prime if and only if the number is greater than 1, and for all positive integers r and s, if n equals rs, then either r or s equals n. An integer is composite if and only if the number is greater than 1 and n equals rs for some integers r and s where r and s are between 1 and n. Basically, a prime integer is a prime is a number with only 2 integer factors. A composite has 2 or more than 2 integer factors. So, is 1 prime? Is 1 a prime number? Nope, because it has to be greater than 1. Is every integer greater than 1 either prime or composite? Yeah. If it's not prime, then it's going to be composite. What are the first 6 prime numbers? Not 9. Yeah. And the first 6 composite numbers are 4, 12. Yep. So, but yeah, so no, prime number is required to be greater than 1. If n is prime, what was that one? Yeah, it's the explanation for B is kind of longer. But yeah, the 2, 3, 5, 7, 11, and 13 are prime. 4, 6, 8, 9, 10, 12 are composite. Okay. Proving existential statements. Proving an existential statement means a statement is finding a x in the domain that satisfies the property. Another way is to give a set of directions for finding such an x. Both of these methods are called constructive proofs of existence. Logical principle underlying such a proof is called existential generalization. All right. It says that if you know a certain property is true for a particular object, then you may conclude that there exists an object for which the property is true, which is basically restating the same thing. Prove that there exists an even integer n that can be written in 2 ways as a sum of 2 prime numbers. What's a number that can be represented as a sum of 2 prime numbers? two different ways. You said 4? 4, it can only be represented one way as a sum of 2 primes. 2 and 1, or 2 and 2. 3 and 1 is not a prime, so can't use that one. Yeah, 2 ways of showing it as a sum of primes. 10. 3 and 7, and 5 and 5. 2 ways as a sum of primes. So suppose that R and S are integers, prove there exists an integer k such that 22R plus 18S equals 2k. Well, 2k is the definition of even number. K equals 11R plus 9S. Factor out the 2, divide both sides by 2. And then you can surmise by the, or conclude from the remaining that 11 is an integer, R is an integer, 9 is an integer, S is an integer, therefore K is an integer, by one of the assumptions that we had at the beginning of the chapter. So, yeah. A non-constructive proof of existence involves showing either 1, that the existence of a value of x that makes q of x true is guaranteed by an axiom or a previously proved theorem, or that the assumption that there is no x leads to a contradiction. The problem with non-constructive proofs is they give virtually no clue about where or how x may be found. And they're hard to program non-constructive proofs. So with the use of computers, it's kind of challenging to make those proofs automated. Disproving a universal statement by counterexample. To disprove a statement of the form for all x that are elements of D, if P then Q, find a value of x for D in D, in which the hypothesis P of x is true and the conclusion is false. Thus, x is a counterexample. Just have to show 1 that to be a disprove it by a counterexample. All you need is 1. A squared equals B squared, but A squared is not, or A does not equal B. What's an example of that? Minus 1 and 1. Yeah. Both squared are equal to 1, but they are not equal to each other. So there you go. Just one example. Just go through the possibilities in your mind, come up with a counterexample, and only need one such counterexample. I remember hearing a story about Einstein. Like 100 scientists claimed that his theories were wrong, and he was asked what he thought about that. It's like, well, if it was wrong, all it would take was one scientist to prove it wrong. So why have 100 scientists claiming it? Why bother with that? All you need is one to prove them wrong. So he dismissed the numbers of people claiming he was wrong. So disproving by counterexample, 1 and minus 1, then you have A does not equal B. Proving universal statements. Method of exhaustion. Use the method of exhaustion to prove the following statement. For all n whose elements of z, if z is even and between is a number from 4 to 26, then n can be written as a sum of two prime numbers. Well, these are all the even numbers between from 4 to 26, and these are examples of them being sums of primes. So it's true. All the possible combinations, all elements in the set can be written that way. You exhaust the possibilities. For large sets, this can be impractical or impossible to do. This is based on logical principle, sometimes called universal generalization or generalizing from a generic particular. To show that every element of a set satisfies a certain property, suppose X is a particular but arbitrarily chosen element of the set, and show that X satisfies the property. So, for example, you have the mathematical trick where you ask a person to pick any number, add 5, multiply by 4, subtract 6, divide by 2, and subtract twice the original number. And the result is always going to be 7, regardless of what integer is picked. What any number is picked, actually, I believe. So, since you can't prove this exhaustively because you can't pick every number because there's an infinite number of numbers, you show this way how the result is always going to be equal to 7. Regardless of what is in the box here. So that is a generalizing from a generic particular. So you can generalize from a generic particular to conclude that the following steps will always get you 7. That you follow the steps, you will always get 7, regardless of the initial value you put in place of X. When the method of generalizing from the generic particular is applied to a property of the form if P then Q, then the result is the method of direct proof, where you first express the statement to be proved in the form of for every X that's an element of D, if P then Q. Start the proof by supposing X is a particular but arbitrarily chosen element of D for which the hypothesis P is true. And then show that the conclusion is true by using definitions, previously established results, and the rules of logical inference. Prove that the sum of any two even integers is even. Well, can't do it exhaustively because there's infinite number of even numbers. So, first, it's a good idea to ask yourself whether or not you believe it to be true. In this case, you might imagine some pairs of even integers added together and check that their sums are even. But you can't check all the pairs of even numbers. Even properties that hold for a large number of examples can still fail to be true in general. So, you need to show that no matter what even integers is given, their sum is even. So, given two even integers, it's possible to represent them as 2r and 2s by the distributive law of algebra. That's also 2 times the quantity r plus s, which is even because r plus s is an integer. Thus, the statement is true in general. Suppose the statement is to be proved is much more complicated than this. What method can you use to derive a proof? Begin by expressing the statement formally. And then ask yourself, how should I start the proof, or what am I supposing? Suppose M and N are arbitrarily chosen even integers. What conclusion do I need to show in order to complete the proof? M and N is even. Since they're both use the term even integer, you must use the definition for this term. It follows from the definition that M and N are even equals twice, each equals twice some integer. One of the basic laws of logic, called existential instantiation, says that if you know something exists, you can give it a name. However, you cannot use the same name to refer to two different things, both of which are currently under discussion. It's kind of like scope in a program. You can't use a variable with two variables with the same name for two different things in the same scope. So, existential instantiation, if the existence of a certain kind of object is assumed or has been deduced, then it can be given as a name as long as the name is not currently being used to refer to something else in the same discussion. The sum of any two integers is therefore even. That's a theorem now. Getting proofs started. How do you go about getting things started? Once you understand the idea of generalizing from the generic and the method of direct proof, you can write beginnings of proofs even for theorems you do not understand. The reason is that the starting point and what is to be shown in a proof depend only on the linguistic form of the statement to be proved, not the content of the statement. So, like the first sentence of a proof and the last sentence of a proof for the following statement would be, for every graph G, if G is a partite graph, G is connected. Yeah. That would be the starting point. Formally restating the question, the idea. The conclusion is just the conclusion of the if-then part of the statement. So the conclusion would be G is connected. So suppose G is a graph such that G is complete bar type. G is show G is connected. So the proof would start this way and end this way. What they don't talk about in this is something that I like to do is sometimes it works to work backward from the conclusion that you're trying to find, where you can kind of meet in the middle, start from what you have, go down, work from what you're wanting to prove and work up and try to meet in the middle, if they meet at all, to prove it. So like here, G is connected. What does it mean to be connected? What's the definition of a connected graph? You know, that sort of thing. Work backward from the conclusion that you're wanting to prove. Fill in the blanks in the proof of the following theorem. For all integers R and S, if R is even and S is odd, then 3R plus 2S is even. Proof, suppose R and S are any integers such that R is even and S is odd. Therefore, by the definition of even and odd, R equals 2N and or 2M, and S is equal to 2N plus 1 for some integers M and N. Then by substitution, you get this form. Then by multiplying it out, you get this form. And then you get this form by factoring out the 2. And then T is an integer because M, N, and 3, and 2, and 1 are all integers because of the, what is it called? The products of and sums of integers are integers. And then finally, R 3R plus 2S equals 2T, where T is an integer by the definition of even. 3R plus 2S is even. So that about wraps up the first section of chapter 4. Is there any questions? We'll get into different types of proofs later on in the chapter. But anyway, have a good day, and I will see you on Thursday.